Hello. I hope this lecture finds you well after probably a busy weekend due to the homework and the midterm happening on Friday. So today we're going to continue with the time-dependent perturbation theory for the Schrödinger equation. And we finished the probability of transition of a system from one initial state to another one. And today we're going to continue on that same line but talking about the Fermi golden rule. So let me share the screen to start the session. Okay, so here we are. Yeah, so let's continue. We're going to focus on a particular kind of potential perturbing the system in a time-dependent way. And well, since we're going to focus later on electromagnetic radiations, it might be convenient to study the effect of a single oscillating frequency that perturbs the system. Because at the end of the day, well, you have electromagnetic radiation, you have basically a sum of different frequencies or an integral if you like, and you can decompose somehow by Fourier analysis the effect of the different frequencies by linearity of the electromagnetic field equations, right? So we're just going to consider a harmonic perturbation of a given frequency. And well, we expected from the previous class that essentially if we were at the Bohr frequency, where the frequency was proportional with this factor of h bar to the difference of energy between the initial and the final state, that we would have the transition. So that can happen. But what we will show at the end of this lecture is that that's one of the cases, but it's not the only one. Meaning that if you are not exactly at that frequency of basically the Bohr frequency of differences in energies, but close to that value, you can still have the transition. It's more probable when you are exactly at the Bohr frequency, but being close yet not exactly at that frequency might still let the transition happen. So, well, again, in the framework of the problem that we were considering, we think that the system is basically in a given initial stationary state until at time t equal to 0, I turn on a perturbation with a switch, and this perturbation has precisely this form, right? So it has an associated potential, Hamiltonian, basically proportional to a cosine, where you have the division between the time dependence of the oscillation and the spatial dependence. So it has this form. I'm just introducing a factor of 2 to get things simpler in the exponentials. And sorry about this. Well, we know how to calculate the coefficients to first order given the Hamiltonian perturbation, which is time dependent at this point. So we're going to plug in this particular formula for H prime, which is our potential of choice, this time-dependent oscillating frequency or oscillating electromagnetic field of a given frequency. And it's going to be, well, proportional to 1 over h bar, the integral from 0 to t of e to the I wfi, where wfi is the Bohr frequency, t prime. And then I simply plug in h prime over here, and it's a sandwich between f and I, right? So there are some things that I can simplify. First of all, I have this sort of separation of variables. And this is a time integral, so I can take the inner product of f with the b of I outside and simply perform the time integral, since this will go out, and using basically inner product properties. So I just have to compute this integral, which in the exponential form is easy to do, which is part of the reason we choose it instead of the cosine, or rewrite the cosine in terms of exponentials. And okay, we have this proportionality factor over here. Then performing the integrals, of course, I have the evaluation of the integral from, well, at t and then at 0 divided by the factor needed to perform the integral correctly. And yeah, I can clean up a little bit the expressions or simply show some sort of symmetry by considering a factor of basically the square root of this, so that I have this level up of terms. And what is important in both expressions is to consider the denominators, right? So I'm anticipating that there's going to be a blow up at sorry, when the denominator is 0, and those are cases that I would like to analyze in further detail later on. So the reason we're doing this is because not only it looks more symmetric, but we can actually express this as a sign, right? Because I have e of I something minus e of the minus I something divided by I. And well, I can simply multiply and divide by a 2. And the factorization of the thingy above will be a sine of this. And then I'll have the denominator divided by 2. So um, this is neat. I have this factorization. And still, the denominators might blow up. And so this is pointing out some sort of resonance condition, if you want to understand it that way. And there are two cases, of course, each one of the denominators, where you can have some blow up, like some resonance. And let's analyze them, right? Of course, I mean, as we expected physically from our intuition, those resonances will happen when you have a perturbing frequency equal to the Bohr frequency, because you're adding exactly the field to encourage transition, like a jump in energies, right? So there are two possible cases, which is what we see from the expressions. The first one is basically if this denominator is 0, right? If this is equal to 0, that means that W, or sorry, omega, is equal to the Bohr frequency omega phi, which we know that is, of course, by this relation, equal to the difference in energies divided by h bar. And well, notice that this term is assumed positive. So this is positive. And well, what we have a transition is basically from a given initial state to another final state of higher energy by this. And this is basically the case when you are absorbing energy from the external field and you have a transition. And that's why this phenomena is called absorption, right? So we're absorbing energy from the external field, which is harmonic, at this given frequency. So, and that is encouraging the transition to go to state of higher energy. The other case, let's say, is when actually you go to a state of lower energy. So if you consider the energy differences, this is negative, meaning that the final state is of lower energy. And well, if you consider, for example, this denominator as being 0, where you would have the case of omega equal to minus omega phi, then this frequency would be positive, and it would be encouraging this transition where you lose energy. And so it helps you to transition from an initial state to one of lower energy. And that is called a process of stimulated emission, because you're stimulating an emission of energy of, say, an atom by perturbing with this external electric field. So it goes to a state of lower energy. It emits a quantum of energy in the process, let's say, and this is due to the stimulation of the external electric field. So again, we descend to a lower state by emitting energy due to the external perturbation. And well, I mean, we can notice that basically this case is different from this other case by basically a minus sign. So mathematically, the analysis of each one of these two cases can be performed in a similar fashion, especially if you look at the formulas, because they're similar in a way. And we're going to focus on basically the case of absorption. And well, we know how to calculate the transition probabilities, which are basically the square of these coefficients. And we're thinking that we're in the case in absorption where this denominator is zero. Therefore, due to the resonance, well, it's, I guess, close to zero. Let's assume for the moment, I mean, what we have done at this point, of course, are equalities, right? Let's assume that we're in the neighborhood close to close to omega fi. Not exactly equal. It might be equal, but we're in the neighborhood, so we're close, okay? So in that case, I mean, since we're basically in the limit where this denominator blows up, this term is way more dominant as opposed to this other one. And we can approximate this coefficient and therefore the probability of transition, which is the squared norm squared of this coefficient, by just considering this element and the norm, right, squared. So if we do that, well, essentially, let's think about it for a sec. We are here, right? This term is going to dominate. Then we have probability of transition norm squared of this coefficient. This is not going to count because this is a complex number of norm 1, so it won't appear. This is going to be norm squared, which is what we have here. The I won't appear because, again, we have norm squared. So that's why we have the proportionality factor of 1 over h bar squared. And we have, of course, the square of the sine divided by this term. Notice that the only difference in the argument and this is basically a factor of t, right? At least inside the parentheses. And we're just going to use a notation which we are familiar with regarding matrix elements, where BFI is defined as F inner product with B applied to I. So in that notation, we simply express this in the same fashion. So this is interesting for the following reason, which is the point that I was stressing at the beginning of the lecture. That, okay, let's consider this as a function of the frequency, right? I mean, we have two variables, formally speaking, which is omega, the frequency, and t, time. So omega is some sort of parameter where I can study how the system performs when I change the frequency of the external field. T is the time of the interaction. So thinking of this just as a function of the frequency omega, of course, this has, well, this is a sinc squared function, right? So this is basically, except for a factor of t, which I should cancel correctly, and that I will do later, basically proportional to a sine of x over x. So, well, in the limit as that goes to 0, clearly there will be a maximum precisely when this goes to 0. So, which is the condition of omega equal to omega phi, which is the resonance in absorption that I was mentioning. So this is a sinc, again. And besides the resonance, what I observe by looking at this function is that the probability of transition is not 0 if perhaps the value of the frequency is not equal to omega phi, but close enough. I mean, this is like a sinc squared function, if you're familiar with that notation of the sinc as a sine of x over x. So it's proportional to it. In fact, I have a plot to illustrate this function, right? So what I did was basically plot this function, well, particularly the sine squared of omega phi minus omega times t divided by 2, divided by the square of omega phi minus omega divided by 2. And just for presentation purposes, I chose omega phi equal to 1. Let's say I was in the units where this choice was appropriate, right? So as a function of the frequency, basically given t, which is fixed, I have this sort of time dependence, right? And well, you'll have the sine squared. And of course, the maximum is precisely where basically omega is equal to omega phi, which is 1 in this case, which is when I have the maximum here. But the function is not 0 outside of this value. So this is telling you that up to the approximations that we have made, the probability of transitioning from the initial state to the final state in the absorption case with an external frequency of the harmonic perturbation not equal but close to omega phi is not going to be 0. So that's interesting, right? Because it's different from, let's say, the discrete jumping energy that we were thinking. Of course, as any mathematical and physical model, this is due to the approximations that we have made, but this is an important conclusion if we stick by all that we have assumed so far. So that is one interesting picture, and the reason I chose it as to present it as a 2D plot is because, well, this function, particularly this one, is a function of omega, the frequency of the external field, and also of time. So you have a given oscillation. You can do the calculation regarding the period of this function if you give the time. But most importantly, well, I mean, so in T, of course, let's say that you keep omega fixed, right? So this is basically the only place where T appears is here. So this is a sine squared. So you have a periodic oscillation, just as it looks like when you follow or move along the T axis. If you consider this as a function of omega for T fixed of the value of the preference, let's say, well, either 10 or minus 10, doesn't make too much difference because you have the sine squared. But, well, essentially, what you have is that you can look as basically the interval around the maximum frequency for which the probability of transitioning is not 0. We're going to call that the width of the function, right? Because again, we're interested in finding the set of frequencies that can uh, cause transition without being exactly equal to the Bohr frequency. So we can do the algebra. The conclusion would be, and just for illustration, basically this is the width that I'm referring to, right? I mean, it's basically the um, interval in which this function, to which the probability of transition is proportional, is not going to be 0. So I'm basically looking at this. And you can do the calculation, and basically this is that this width that we're going to call delta omega is equal to 4 pi divided by time. And t is basically the value that you choose once you go over the 1D plot, right? So you choose t fixed time, then you look at the width, and you have this result. And also for completeness, if you want to investigate the period of the function, remembering that it's squared, so it's different from just the sine. The period of the sine squared part, regarding this as a function of time, is 2 pi divided by omega phi minus omega. So that would be the period of this function, right, from here to here. So for the purposes of the physical analysis we're going to do immediately, we're going to call this t, which is basically the time of interaction, if you follow what was the notation for p in this case, we're going to call it delta t, because at the end of the day is the time we observe the interaction, or we allow to basically have this perturbation from the unperturbed state at t equal to 0. And we monitor if we will have a transition or not. So this interaction time of observation is going to be called delta t. So please look at this figure in detail later on when you look at the lectures. And given that we have this, and we have called this t delta t just in this notation, and you'll see why. Well, we have that, excuse me, the product of delta omega, the width, with delta t is, well, actually equal to 4 pi, but the order of 4 pi, right? So this reminds us of the sort of uncertainty relations we know from the Heisenberg principle. And well, if you are a math person, this is basically Fourier frequency time uncertainty relation, right? That happens with Fourier transforms. And for that, you know that basically the Gaussian is the one that minimizes the uncertainty in both spaces. If you think as a physicist, of course, you're thinking, okay, I have an uncertainty principle. I can actually remember basically the energy time uncertainty principle if I remember, well, that I have a linear relation between the energy and the frequency given by this. So the proportionality factor is h bar. And if I do that, basically, I simply multiply by h bar to get this, which gives me this. Of course, if we do a very coarse approximation, pi is of, well, close to 3. So this is approximated like 12 h bar, which, okay, perhaps is 10 times, but it's of the order of h bar, right? And so there is a physical interpretation of this formula beyond the math of the Fourier space, which is that the observation time reduces the uncertainty in the energy. So if I stick long enough observing like the delta t, I will get a better measurement of the energy at some point. And well, I mean, either in this relation or this one, when delta t goes to infinity, which is the limit that we will perform, then delta E or delta omega, the uncertainty in the energy or the frequency will go to 0. And in this case, if I monitor what happens in the limit as delta t, which was actually t, if you remember, goes to infinity, basically I will do the analysis of this, right? So I can, well, multiply and divide conveniently for the t to have something in a polished form that I can analyze. And if I do that, well, basically, precisely, right? So I look for this formula, then multiply and divide by t squared to get this, and then basically noticing that in the limit as t goes to infinity, there will be delta function popping up with a given proportionality factor, which will eliminate a factor of t over here. This is going to be the factor that I knew from the matrix element and divided by h bar squared. Then 2 pi coming from the analysis of basically Dirac delta distributions. In terms of the areas, there's also a t, which is happening after cancellation with the t squared term. And well, this is a t multiplying a Dirac delta. So of course we expect the Dirac delta basically, just imagine, right? In the limit as we basically make t go to infinity, for example, right? When we go far away in this plot. So, well, we have a distribution. We know those are complicated objects, but, well, there are two conclusions. The first one is, yeah, we're getting blowing up in the probability of transition in infinite time. It's actually quite localized in the sense that you know that the Dirac delta is basically 0, except for the case where omega is equal to omega phi, where this set it is infinity. The reality is that this is a little bit more complicated. Mathematically, this is a distribution, and it's something different from a function, but never mind. It's not important. Right? We can stick with the zero infinity interpretation of the Dirac delta. And yeah, I mean, this is probability of transition after a very long time when we make t go to infinity. But most importantly, we see that, well, of course, I mean, we would have to perform the limit, etc. But at this point, before I perform the limit, this is proportional to t. So actually, if I were to consider the rate or the transition rate, which is basically a rate of change with respect to time of this probability of transition, that's the way it's defined. So this is the definition. R is going to be the transition rate of change with respect of time. So derivative of P, and derivative of the probability of transition with respect to time. So, I mean, if we notice that basically if I pass this to the other side, in the limit, this quotient becomes 1 as t goes to infinity. Well, I mean, heuristically, what we'll have is that the limit of this derivative or this rate or this transition rate will be due to the proportionality in time that we have over here, basically In the limit, it will be equal to, well, 2 pi divided by h bar squared, the square of the matrix element, and then the Dirac delta. So we eliminate the time dependence over here in this way by analyzing the rate of change, where heuristically we take derivative with respect to time. And so again, this is telling you that the transition rate of change is localized in the sense that it works like a delta function. So um, now in this limit, as opposed to the other case, we do have the transitions just when the frequency coincides exactly with the Bohr resonance frequency. So only in this case, in this approximation, of course, we are always subject to the approximations that we have made. And that's important for you to understand as a physicist and as an applied mathematical modeler person. So in this approximation, the transition rate formula is telling you that it will happen in this approximation only when the frequency is equal to the Bohr frequency. So yeah, in this case, in this approximation up to this point, where we have made t go to infinity, you'll need the quantum of energy of the Bohr frequency or Bohr energy to jump and to do this absorption process. Again, of course, it's approximate, but in reality, the situation is more complicated because usually what happens is that the allowed states are not discrete but a continuum. And so we're going to obtain that but by basically introducing this complexity in the model. And by assumption, we're going to think that the allowed final states, which are the higher energy, it's not a single one, but there rather are a continuum which are close to this maximum. So it's going to be a small interval where you can have the transition, but it's still not a single one. So we're just going to allow ourselves to do that. Okay. So basically, we're going to call to epsilon. Bear in mind that this epsilon has no relation with the parameter that we used in time-dependent perturbation theories. I'm just running out of letters essentially. So the length of the allowed energies as final states will be 2 epsilon. To have an interval um, around basically the final energy of minus epsilon plus epsilon in that location. And well, we're also going to assume that this interval is small enough that so-called density of states, which I might have started talking about before, is going to be continuous in this interval because it's very small. So of course, I'm assuming continuity of the density of states of energy. And well, I'm going to assume that this epsilon is small enough that the values of this formula for the density of states do not change too much. So if you remember, the density of states is such that this density times d is the number of states within the interval e or e plus d. So this is, of course, a differential approximation. I'm thinking of d as this differential element, which is very small, but that's the way calculus works, and I'm allowed to use it. So again, I'm basically sitting in the final energy and drawing an interval of length 2e around it. So that's why I consider the integral EF minus epsilon, sorry, 2 epsilon. And then EF plus epsilon around it. And well, I'm gonna put a condition such that the Dirac delta doesn't vanish in this interval. And that is simply choosing well my zero reference of energy. So we know this relation, the energy equal to h bar omega. And we're going to make the assumption that basically this Bohr energy, EF minus EI, which we have seen is proportional to h bar omega 5, is within this interval. So this is the condition of being within the interval, which if and only if happens if basically the initial state is in an interval of length minus epsilon. So this will happen if basically I am choosing as my zero energy reference level the energy of the initial state, which is well allowed. Energies are defined up to a constant because I can always switch the zero reference energy level. And you'll see why I need this assumption in order that the Dirac delta doesn't vanish. I think perhaps it's just to be careful mathematically, but especially if you're seeing this calculation for the first time, it's worth to look at it in detail. So I have this formula, and instead of having these, I'm going to have this term integrated over the interval of allowed possible energies, since I'm assuming that there is not basically a jump into a single frequency, but rather a set of continuum states allowed as final energies. The physical situation in the particular application that I'm dealing with might be such that that happens. So this is why I'm using this term and integrating over this interval, basically this interval, and using, of course, the density of energies, because now it's not just a single energy, but the span in this interval. And there might be simply more states in a given energy, and that's why you need the density of states. Now you'll see how the assumptions that I have made so far are gonna help us. So the first one is that we thought this epsilon was small enough such that this function, which is assumed to be continuous, is almost constant over this interval. So I'm going to take it, and because I'm integrating over an interval around EF, where the epsilon is very small, I'm going to simply take out assuming continuity of the density of states. And, well, I'm just going to assume that the values are very close to the density of states of this final energy, because we assume that epsilon is small. So that's the first step in the assumption. The second will be using what I stated right before, which is that, well, this is a Dirac delta. So in principle, I have no guarantee that it won't vanish in the interval of integration. That I have to be careful. But I mean, if I'm careful enough such that basically EF minus EI is in this interval, which is equivalent to omega phi, well, because it depends proportionally to this, to be in this interval, then Dirac delta won't vanish. And in fact, this integral will give me 1, provided that I have done the appropriate Jacobian of the transformation to go basically from the energy space to the frequency space. That I have taken care of. And that stands for a factor of h bar, which I have over here, because you have this linear relation, in fact, proportional. So that just amounts for the Jacobian. And so this term is being taken care of here. This Jacobian is being taken care of here and here. And then this is equal to 1 by assumptions of choosing an appropriate energy reference level. And then I have this. So this was 1. And in this application problem, where I have allowed a continuum of states in a very small interval to be the final destinations of the transition, I have this formula. So the transition rate in the approximation as the observation time goes to infinity, well, of course, I have these factors, nice constants, but I have it proportional to the square of the matrix elements, and I also have it proportional to the density of states in the final energy. So this is a very famous result, this calculation of the transition rate, and it's called the Fermi's golden rule. So again, this is proportional, or this transition rate is proportional to the square of the matrix element, norm squared, excuse me, and times the density of states at the final energy. So I'm iterating what I had said, excuse me. And well, usually we care also for, in addition of the transition rates, which might appear if you basically follow the time evolution of the problem, for the probability of transition after a very long observation time, meaning that t goes to infinity, which is equal to the square of the coefficients to first order by all what we did in last lecture. So that is approximate. Well, of course, we have this T proportionality factor, which was the moral of the story of defining the transition rate and basically considering this. So I have this times a T. And so this is something that might not be mentioned sometimes in a physics book, but this is something quite important to mention, though, especially if you want to be proper mathematically, which is that, well, I'm assuming this limit of infinite observation time, right? That's why t goes to infinity. Now, this coefficient, which is equal to this one squared, is proportional to time, and t is going to infinity. So clearly, um, well, this coefficient is going to become big enough. And so remember that in the process of perturbation theory before, at some point, we made epsilon equal to 1. So when epsilon was equal to 1, well, the only assumption of the perturbation being small is related to, first of all, the size of the Hamiltonian matrix perturbation coefficients, and also to the size of the coefficients themselves, right, of the projection. So this is telling you that the limit as t goes to infinity, somehow time-independent perturbation theory stops being valid if you have made the assumption of epsilon equal to 1. I'm not saying that this is a bad model. Of course, it's a good approximation up to where this doesn't grow too much. So t going to infinity might mean a finite time for the purposes of the lab or the experiment. But I want to point another way where you, or in which you can perhaps control this happening. And so that is if basically you don't make the parameter epsilon go to, sorry, make it equal to 1, but you rather make it small enough as you need. So in practice, in the lab, we will not sit in the lab measuring the experiment for infinity, right? I mean, we'll stop at a point. And well, that of course tells you that the perturbation has to be small, but you can have certain control with the parameter epsilon into, for the desired observation time, to have the Hamiltonian perturbation and the associated coefficients to not blow up and to be controlled at some point. This is perhaps just a mathematical uh, understanding of the problem. Maybe I'm being more careful than usual, but I just want to say that, well, it's true with epsilon equal to 1. At some point, this approximation of t going to infinity won't be valid, but I mean, I'm not criticizing the technique. In fact, I'm trying to defend it in the sense that if you do not stick with the choice epsilon equal to 1, but make it small enough for the observation time long enough as you desire, being finite still, though, you might be able to solve the problem. Of course, you might have to recalculate some things because at some point, the reason we made the epsilon equal to 1 was to simplify the expressions for these coefficients, and particularly to first order. And for that, you might have to go to the notes and recalculate some things. I mean, I'm not going to make your life complicated, but it's just important to consider where the model might need us to be a little bit more careful. So regarding the Fermi golden rule, this is all what I want to present today. I will go into more detail on the particular interactions that I want to talk about, which is basically hydrogenic atom, uh, simply perhaps just hydrogen, interacting with a given electromagnetic field, and a very famous approximation called the electric dipole approximation, but that I will do later in the week. For the moment, I think the section on Fermi golden rule is enough for you to process and study with your notes, and you also have an exam coming up. So read the section, use the information that we saw in the previous lecture on Friday. And yeah, I mean, if you have any question, again, either for previous homeworks or the next midterm coming up, or even this material, feel free to either send me an email or come to office hours. So I'll be happy to help you in any way of contact you desire. And well, best of luck with your study, and see you very soon.